In this lecture, we learn about the organization of a computer, and also we learn about how memory is addressed in a computer. So, in a simplified version of our view of a computer, we can think of a computer as having a processor and having memory. The processor has several registers inside that are places where we store data inside the processor. In the case of RISC-V, there are 32 such registers. The memory has many more positions to store data, and the memory is simply an array of bytes, and each piece of data in memory has an address. And in this representation on the screen, we notice that the addresses change in intervals of 4 between consecutive addresses, which means that each one of these boxes is storing 4 bytes. So that's why we go from address 1000, 1000 to 1000, 1004, 1000, 1008, and so on. The computer also has an address bus. The address bus is used for the processor to send the value of an address to memory to specify where in memory an operation should take place. And the computer also has a data bus that is used to communicate data between the memory and the processor. There is also a control bus that's not shown in this picture. The processor has a program counter that is a special register inside the processor that's used to indicate which is the next operation that will be executed. And the processor also has an internal register called an instruction register. The way instruction execution will work is that initially the processor will gonna ask the memory to send the binary code for an instruction, and that binary code will be initially stored in the instruction register so that the processor can then decode that instruction and find out what's the operation to be executed. The processor also has an arithmetic and logic unit called the ALU. The arithmetic and logic unit is where all the add, subtraction, logic operations, shift operations will take place. RISC-V is an instruction set architecture that was designed at the University of California at Berkeley by Krista Azanovich with collaborations with David Patterson. Krista decided to create this architecture during a summer when preparing to teach an undergrad class at UC Berkeley. And then later on, it became a research project and became a very widely adopted architecture. There are lots of articles in the press about RISC-V. I encourage you to search for very current articles about RISC-V. And here is one example of one from a year or so ago. But there are many more new news about the RISC-V, and it would be very good for you taking this class to be well informed about RISC-V. With the competition between the United States and China, RISC-V is becoming a very important element in the development, independent development of processors in China. So let's start our review of the organization of our computer with arithmetic operations. And let's look at operations that we call three-operand operations. They have two source operands and one destination operand. So one example of such an operation is an add operation. In this example, we are adding the value of C to the value of B and storing the results into A. The way we would express that as an assembly instruction is as shown on black on the left, add A, B, C, where B and C are the source operands and A is the destination operand. What you have on the right, that after including the sharp symbol, but anything after the sharp symbol is a comment in assembly. It's not part of the program. So there are two source operands and one destination operand in this add operation. We may also add a constant to a value or to a register in the processor, and in this case, the operation becomes an add I operation I stands for immediate, so we are adding an immediate value. In this example, we are adding the value 20 to B and putting the result into A. We can also have a subtraction operation. For example, we can subtract the value of C from B and put the result into A. We can add a negative constant to B and put the result into A. So these are some examples of 3 operand instructions that we have in RISC-V. Now let's see how we generated the assembly code for a simple C assignment statement. So in this C statement, we have to first compute the value of G plus H. We're going to do that and put the result in the temporary register that we're going to use T0 for this. Then we'll compute the summation of I and J and put the result in another temporary T1. And then we can subtract the value of the 2 temporaries and have the result into F. So this is the sequence of operations that you'd execute in an assembly version of that C assignment. However, this sequence of operations could not be executed in a RISC-V processor or even in a RISC-V simulator because the processor does not know what F, G, H, I, and J are. Those are variables that appear in the source C code. So in order to produce code that the processor can execute, we have to map those variables into registers in the processor. And in this case, we map the variables into registers S0 to S4 as shown on the slide. And now what we do, we rewrite that program, but where we had G and H into the instruction, we are replacing by the corresponding registers where those values should be found. And notice that in the comment that appears in red to the right of the instruction, we maintain the G and H. It's very important to use meaningful name of variables in the comments of an assembly program that you are writing and debugging by yourself, because that makes it much easier to understand the program. And then we do the same to the second addition operation. We replace the I and J with the name of the registers. And finally, we do the sub and we put the result into the register that corresponds to S0. So now we have a piece of assembly code for RISC-V that actually could execute in a RISC-V processor. The compiler or the assembly programmer is the one that decides which registers are allocated for which variables in a program. So there are register operands. Arithmetic instructions use these register operands. And in RISC-V, there is what we call a 32 by 32 bit register file. What this means is that there are 32 separate registers in RISC-V, and each one of those registers stores 32 bits. So we call this a register file, but it's not a file in the same sense as a file in operating system. So these registers should be used for frequently accessed data or for data that is very likely to be accessed in the near future. The registers are numbered from 0 to 31. And a word is formed by 32 bits, so each register contains a single word. And there are assembler names for these registers. T0, T1 to T6, for example, is used for temporary values. S0, S1 to S11 for saved variables, and there are other types of registers that we're going to learn in the next lectures. In the textbook, the notation used for the registers is from X0 to X31. However, in this course, in all assignments and in all labs, we're going to use their assembler names instead of using the notation X0 to X31. Now let's consider how we address an integer array that's stored in memory. So an integer array is simply a sequence of integer values. In this example, we have an array A, and this array A has 8 elements, so there are 8 integers stored into the array. Let's assume that those are the values stored into the array. Now let's look at memory. And first we note that in this drawing of memory, the addresses increase by 1. So we go from 1000, 1001, 1002, etc. So each one of these boxes drawn on the screen contains a single byte. Let's assume that this value, that's the value 1, is at the address 0x1000. The way and let's assume that this is a little Indian machine. So if this is a little Indian machine, and the way we say if the first element of an array is at a given address, the way we describe it, we say that the base of the array A is at that address. So in this case, we say that the base of the array A is at 0x1000. Because this is a little Indian machine, we're going to have the little end of the number per first at the address 1000, follow in 1001, 2, and 3 with the other bytes in the number with the big end of the number at 1000, 1003. So this is where the number 1 will going to be. The number 3 will be next to it using the same byte order, and so on for the other numbers into the array. So this is the way the array will be stored in memory. So now that we have seen that that's the way the array is stored in memory, we can look at the corresponding address for each one of the elements of the array. The element 0 of the array is at the base of the array, that is the address 0x1000. The element 1 of the array will be at the address 0x1000, The reason that there is a skip of 4 between the base of the array where the first element is and the element 1 of the array is because each element has to occupy 4 bytes, and each byte has its unique address in memory. So following, we have the element 2 of the array at the address 1000, 1008, the element 3 of the array at 1000, 1000C, and so on. So here is a different representation of memory, where now we have the distance between each box to be before. Therefore, in each one of these boxes, we have 32 bits or 4 bytes. So each element of the array is now stored in one of these boxes. And in this case, we can write on the paper the representation this way, which is much easier for us as humans to read. So a word is the unit used to communicate between the processor and the memory. In RISC-V, a word has 4 bytes or 32 bits. And the processor, as we saw before, has several registers. In this example, let's just consider one of the registers of the processor T0. And then we have memory, and memory has several different positions. So how do we transfer data between the memory and the processor? So let's look at this example where I'm going to use the different colors in this slide to represent the different values that are stored in each one of the memory positions and in the processor. So first, let's consider the problem of bringing a value from memory and putting into the register T0 in the processor. The instruction that we're going to use to do that is called the load word instruction. It's load word because it's going to bring a word which is 32 bits from the memory and put into a register in the processor. So it's loading from a specified memory location into a specified register in the processor. So that will be the action that will going to happen. A given value in a location specified will come from the memory going to the processor. The complementary instruction to that is called store word. Store word will store a value that's currently in a specified register in the processor into a specified memory position. For example, we may take that value that is in T0 now and put into the memory position at the address 1000, 1008. This sequence of 2 operations where we loaded from the address 1000, 1004 and store into the address 1000, 1008 with the typical sequence of instructions that we use to copy values in memory. So if we go back to our array example, let's consider that now I have a C statement where I wanted to add the element 2 of the array A to a variable age and put the result into the element 0 of the array A. So our assumption will be that variable age is at S2, and the base of array A, the address of the base of the array A is in S1. That's what that notation means. So if I want, first I need to load the value that is in the position 2 of the array A, And for that, we're going to use the load word instruction. The destination is the register T0, and the source is the memory location given by the expression 8S1. 8S1 means that I'm going to take the address that's in S1 and I'm going to add 8 to it so that I can get to the element 2 of the array. So if you're wondering why I'm using 8 when I want the element 2, is because each element has 4 bytes. So every time that I want to advance by one element, I have to add 4 to the address. So what we're going to happen in this instruction is that I'll take a value from the position 1000 1008 in memory, and I'll bring into the register T0. Now the next instruction, we're going to add to that value, and so a new value is going to be produced in T0. That will be the addition of the element 2 of the array with the variable age. And then I'm going to store the result into the position 0 of the array. For that, the displacement that I need to add to the base address of the array is 0. So the instruction will be specifying that I'm storing a word from T0 into 0S1. And what that will do is to bring the new value into 1000, 1000. So let's take a closer look at these instructions, and let's learn the terminology that we use to describe them. 8S1 is the address of the source memory location for the load word, and T0 is the register that is the destination of the load word. For the store word, T0 is actually the source register for the store word. The value is coming out of T0 and going into the memory. The destination is in memory. The address of the destination is given by 0S1 in this case. So this is called the displacement addressing mode. What that expression does is to get the value stored in register S1, add 8, which corresponds to 2 words to this value, and then the result is used to address as the address for the load instruction. So registers are faster to access than memory, much faster than memory. So whenever possible, we should try to do our operations from registers and into registers. So if I operate with memory, I need to have loads and storage instructions, so more instructions are executed. Any architecture like RISC-V, where it's impossible to do an operation with memory, you cannot add to a value that's in memory. You have to first load the value from memory, perform the addition, and then if you want the value to be somewhere in memory, you need to store it back. So that's called a load store architecture, because you always have to do loads prior to the operations that you want to execute, and then after you obtain the result, you have to do stores to store back into memory. So the compilers must use the registers for variables as much as possible so that the computation is more efficient, and should only spill to memory for less frequently used variables. So the process of allocating registers for the different variables in the program is a very important task that the compiler does. And there has been research and work done into improving the optimization of registers for more than 40 years. And there is an extensive number of research papers that have been written into how to optimize register allocation. We can also have immediate operands. For example, I could have an add I, that is an add immediate, that will be adding the constant 4 to the register S3, and in this example, putting the result in S3. There is no subtract immediate instruction because I can simply add a constant, for example, -1. And so the value of the immediate that appears in the instruction will appear in 12 bits. And will be sign extended to 32 bits before it's added, in this example, to S1. So there is a design principle that we need to consider here, is that it's a very fundamental design principle in computer architecture that says that you should make the common case fast. So the common case is that there are lots of small constants that appear in programs that we write, and allowing for immediate values in an instruction makes that I don't need to have a load instruction to load that constant from memory and put in a register, then issue a second instruction to do the operation. I can operate directly with a constant, and that's the reason to have the instructions such as the add I. We're going to see other instructions that have immediate values in future lectures. And then we have memory operands. Memory operands can be used, the memory in general can be used for composite data. For example, we already saw the example with arrays. We can also have things like strings in memory or compounded data structures that are common in C can be stored in memory. So memory is byte addressed. There is one separate address for each byte in memory. And each address is identifying one 8-bit byte. Remember, a byte contains 8 bits. The words must be aligned in memory because each word is 4 bits. You cannot start a word, for example, at an odd address. Every word has to start at an address that's multiple of 4. In this slide, we have highlighted in bold the addresses in this part of the memory range that where a word can start. You can never start a word in the middle, such as at a multiple of 2 that's not a multiple of 4. We can also represent memory in this fashion, which makes it easier for us as humans to read the values that are stored in the different positions in memory. So in this lecture, we have learned that we have a machine organization, a computer organization that has a processor. The processor has registers. In the case of RISC-V, it has 32 such registers. We have learned that the processor also has a special register called the program counter that's used to determine where the next instruction for execution in memory. There is an arithmetic logical unit in the processor, and there is an internal instruction register. The instruction register that is used to store the binary representation of an instruction as soon as it comes from memory. We also have learned that there is an address bus for the processor to specify where a memory operation should occur, and a data bus to communicate between the processors. We have learned that memory is addressed by bytes, that if I have an array of integers, the difference between two consecutive addresses of elements of the array will be 4. And we also have learned about the addressing for loads and stores, such as the displacement addressing that allows me to add a constant to a base address.